Hey everybody, and welcome back to Calc 3 Online. So the plan for today is to talk about something called surface integrals, which are really not too bad if you understand line integrals really well, because these are really just, like I write right here, they're basically just the 1D up version of a line integral. So, a line integral, just, quick review, is basically you could have any sort of curve, like down in XY plane or something. And then you have some sort of, you could measure some sort of area between a space curve and that projection of the space curve basically down on there. And so this idea, right, if you just let it kind of go left and right in a sense and just give it some dimension, kind of perpendicular to the curve. And so in the sense what I'm saying is instead of a space curve, you have some sort of surface, right? Basically you can kind of think this one line or something was like the space curve. Now I'm just saying let's let it go left and right from there. But if we do the same idea where we measure how much stuff is basically above or below this and, the plane down here, then that is what a surface integral is. It's really just the 1D up version of a line integral. And so it's probably not hard to believe that instead of doing this is a line integral, right? Instead of a line integral where you just have one integral, we're going to have two, okay? And before we just did f of r of t, but, just like we had to parameterize surfaces, we know that there's two inputs for that. We would now have f of, let's just do, r of u and v, okay? And so that's just like a parameterized surface, right? And this also will scale up in dimension. So this is just like a one-dimensional, this is just like a tangent line basically to the curve at any spot, right? But now we have to pop that up a dimension too, and the way we can do that is just times it by the magnitude of r with respect to u cross r with respect to v. And then this also scales up. This was, these infinitesimally small little one-dimensional chunks of the curve down here. And now we have a dA, right, which is like infinitesimally small little patches, right, like little squares. And that's what we're doing the integral over. And so that's it. That is actually how we do the surface integral. We just do f parameterized now with a surface parameterization, and then we multiply it by the magnitude of a cross product instead of magnitude of r prime. This is something we saw before too, where if we do like a line integral of just ds, it basically f of x was just like 1, right? So there's like a 1 in there. If we do the integral from a to b of magnitude r prime of t dt, that is just arc length, right, of this arc down here. And turns out that this is actually the same, this can also scale basically really nicely. If you just do where f of xy equals 1, so the surface is just a 1, then you're going to get double integral, right, over some region, magnitude ru cross rv dA, and that is just the surface area of the thing down here in the xy plane. It would just be, if you projected this down, it's just calculating the surface area down there. This is something we've actually seen before, and we saw it, I think, in chapter 15 for the first time. But that truly works that way too, which is nice. I wanted to say just a little bit about this magnitude cross product thing that's popping up. So just to make it more clear, so when we do a line integral, right, we're doing a line integral over, some sort of curve. This is down in the xy plane. You want to think, the line integral is above this, or it could be below it too, but let's just say above it, right? And we're calculating the area basically above that. And the idea with the derivative here is that basically you're taking like a super small little chunk and you're approximating that chunk with just a tangent vector, right? That's what the r prime, magnitude of r prime thing does. So, you have, again, like infinitesimally small little piece of the curve, and then if you zoomed in, right, if you zoom in and this chunk is small enough, it can look straight, right? And it can look like magnitude of r prime. So that's like why we can do the integral that way, because we're basically just chopping this thing up into super small little parts and approximating it with these little tangent vectors. Over here, it's the same idea. Like if you, and I'm actually going to show you like a few slides that we've actually worked through before for this, but if you think back, we've done this thing before where if we have a surface, we can like approximate a little square, like this blue square, by doing a tangent vector, say like r with respect to u, right? And then a different tangent vector, like over here, r with respect to v. And the area of this little piece in here would be the magnitude of RU cross RV, right? That's something that goes back to, our vectors unit in the beginning of the year. So the idea here is the same idea over here. We're basically talking about a super small, infinitesimally small little piece, and the idea is like any little patch on the surface could basically be approximated by the tangent plane, okay? So here it's the tangent, like vector, like line, right? And then here, it's a tangent plane. So the tangent plane acts as a good approximation of the part of that surface, just like the tangent line acts as a good approximation of the curve here. And we've actually gone through all this calculation before, so I'm not going to go through all this again, but this is like a better picture of what I'm talking about. These should look kind of familiar. We've seen this before. I walked through before what r with respect to u and v are, and you get these tangent vectors in different directions, and then we want the area of this parallelogram, which we're going to need to do a cross product. And so you get all this stuff. But I'm not going to go through all of it again, but basically we're just doing, this. And this kind of gray rectangle is as close as we can basically get to the blue one which is actually on the surface, okay? And if you zoom in far enough and you have a small enough grid, right, that gray thing really will be close enough. So it's like an approximation, but it's a good approximation. Integrals are always approximations. So let's compute one of these things. So I want to compute the surface integral of x squared ds, where s is the unit sphere, okay? So just like line integrals, a lot of times the hardest part in doing a surface integral is computing the parameterization. This part in here can be like really tough sometimes. Now, this is a unit sphere, right? So that one's not so bad, but there's lots of them out there that actually are pretty bad. For the unit sphere, we should just use spherical coordinates. That's basically how we do it. And since it's a unit, the row that's in spherical coordinates would just be 1. So we would get this parameterization, right? So, you're used to having a row in there, but it's a unit sphere, so that's just 1. So that's my parameterization, which honestly can be sometimes the hardest part, which is nice that we don't have to really worry about it here. Then just like a line integral, you basically go and just start plugging stuff in. We have x squared, right? So this is my x, and so I'm going to have to square that thing. So sine phi cos theta, all of that squared. And then the magnitude of RU cross RV, right, is just really the Jacobian of given these this parameterization, which we know is rho squared sine phi. But again here, rho is 1, so we're just literally going to get a sine phi, right, out of that. And then we just need to do d phi, d theta, and that's it. And so now it's just a matter of computing the integrals. So it's actually one that we can split because there's just a phi and there's just a theta. So if I split it, oops, I didn't even split. So my theta integral is running from 0 to 2 pi, and then I'm just doing cosine squared theta d theta, and then my phi is 0 to pi, and it's going to be sine cubed phi d phi. Right, because you get the sine squared phi in there, and then you get another one. And then you basically just do some trig identities. We can do this integral, and, hopefully at this point we're feeling pretty good with this stuff. Since cosine squared x equals like 1 plus cosine 2x over 2, that's how I would do this integral. And this one, I would do like sine squared, let's just do x, I guess. Sine squared x times sine of x, right, is sine cubed of x. And then you can do sine squared is 1 minus cosine squared, right? And the way to do that integral is, so when you multiply in the sine of x, right? Now, so that is basically what we could put in there, right, with thetas really. But this integral, of course, is nice and easy. And then this one, you can just do u sub. Here you would let u equal cosine. And then the derivative of cosine is in there. And so that's kind of how I would do that one, personally. Whatever way you want to do it, basically you're going to get the following. So just going through what I basically said, I would swap this out for 1 plus cosine theta over 2. And then that's a nice integral. And then same tricks here, and I would do u sub. But long story short, you get 4 pi over 3. But the way you want to think of that is it's literally like, when we do a line integral and we get this kind of picture, right? We're just sort of looking at how much stuff is above or below the thing, right? Well, now we're just talking about a sphere, right? And I'm, just doing the same thing. The idea is how much stuff is above or below the sphere, it works the same way as a line integral. So if you understand your line integrals, you really should see the connection here and be able to do surface integrals. They're not really any different. It's just like if I could draw, a surface, right, over this thing. And so now I would just do the same idea, and I would just check how much stuff is basically below, the surface. This is a horrible picture, but that's like the idea. So, yeah. And this has tons of applications all over in a lot of physics and things like that again, but they're very, very commonly used in a lot of sciences. So one of the things I just wanted to make a note about for the parametrization stuff, a lot of times we get, we actually call these things graphs in math. If you can write like z as just a function of x or y, some of the computation gets like a little bit easier, and you might want to I hate the word memorize, but you might want to memorize what this thing is, and it actually will look fairly similar. So here, let me just kind of go through this. So r with respect to x, if you can just parameterize it as x equals x, y equals y, and then z is a function of x and y, we would just get the vector, we'd have 1, 0, and then, g with respect to x. And then r with respect to y, right, would just kind of flip the 0 and the 1, and then we would get g with respect to y. And literally, if you go and just do, the cross product, I, j, k, and then you put it 1, 0, g with respect to x, 0, 1, g with respect to y, and you just do that cross product out, you're going to get negative g with respect to x, negative g with respect to y, and 1. And so the magnitude, right, is actually something that kind of looks familiar. It's just the partial of z with respect to x squared plus the partial of z with respect to y squared, looks like a 2, plus 1. And, this should look pretty similar because if we again had the function be just a 1, right, then the double integral where this is a 1, this is exactly how you compute surface area, right? Just like this is how you compute arc length, right? You just take the partials here. Now here it's just ordinary derivative, but that's because there's only one thing to differentiate. But yeah, it's just it should look familiar because we've seen this before with arc or surface area. And like the surface integral, so double integral of the function with respect to s, in total general, right, would just be a double integral f. You would still have to parameterize, but x is x, sorry, and y is y, but then z is the g of xy. So that would be like my parameterization, right? And then I would just multiply it by this thing. So I would have square root partial z with respect to x squared plus partial z with respect to y squared plus 1. And then I'll just put it here, d8. And so that's your, magnitude cross product r with respect to x cross r with respect to y. So you might want to kind of memorize this surface integral formula because this is what we would use if you can ever write z as just a function of x or y. There are similar things where just some of the letters switch around. If it's a function of, say you can write y as a function of x and z. So there are other variations on this, and if it's a function where, here, I'll just write one down. So if it's a function where y can be written as x and z, you would get the following. So if you look at this, just some stuff kind of shifts around. We're writing here z as a function of x and y, but now y is a function of x and z. And in here, the magnitude cross product part was z squared, z with respect to x squared, z with respect to y squared. But now, of course, it would be y with respect to x squared and y with respect to z squared. And the signs will all work out nice because you're squaring things anyways. And then there's another one that you could get if x could be written as a function of y and z. So that's just another way to do it. And it's really just a byproduct of nice, simple partial derivatives, really. So, last thing I want to talk about is surface integrals over vector fields. So we did that with line integrals, right? We did f.dr thing. Turns out you can also do f.ds. And we really do write it like this. We do f.ds, and the s is sort of bold, like the r was bold when we did line integrals. And this kind of thing where we're starting to think about a surface integral over a vector field is actually something special that I will formally define on the next slide, but that's actually called Flux. And these flux integrals are only computed on what we call closed orientable surfaces. And the easy definition is just that it's things that have an inside and outside. This is something called a Mobius strip. And a Mobius strip is a classic example of something that doesn't have a inside and an outside. It's actually a one-sided surface. If you're on the outside here, right? So I'm around the back side there now, right? Notice that because of this weird twist, so now I'm on the face, you can see. But then I come in here, right? And I'm flipping to the inside. And so I just went to what we kind of think of as inside. Now I can see it right there, right? And then flip again. So it's just going to keep doing this. And so you literally can just go around and around and around and around, and you never get to a different side. It's truly a one-sided surface. But and there's other ones. There's something called here, I'll write the names of these down. So this is a Mobius strip. This is something called a real projective plane, which I'm not going to get into. This is a kind of a neat object in the field topology, which is what I studied in grad school. And you actually define it by just mapping, identifying lines through the origin in a certain way. And I could explain it to you if you want. But there's lots of other things that are not orientable. The things that definitely are definitely like a sphere, right? You can talk about everything that's orientable really nicely with normal vectors, and that's why all these arrows are here. So if you have some sort of closed surface, and you can always have the normal vector sort of pointing in two different directions, on the outside of the sphere, right, they could like point out like this, or you could, at those spots, right, you could point in towards the inside of the sphere. That sort of conceptually what it means to have two sides, right, an inside and an outside. And those things are nice objects in math. They're really easy to work with. And the convention is that when the normal vectors point out like this, that is a positive orientation. Stuff is sort of leaving the space. When stuff comes in, there's a negative orientation, okay? I sort of think of it as like sinks and sources, right? There's like a source of stuff coming out here, and there's a sink of things going in. And in my mind, I would think sink negative, source positive. There's a net leaving area. There's a net amount leaving, whereas here there's stuff coming in. And for those of you that want it, to me, this is the formal definition of orientable, but way beyond our course. This says a surface, an object, is orientable basically if and only if H1 of S, which is the first homology group of S, has a trivial torsion subgroup. There's a lot of words there that probably make no sense. But that is actually the formal definition, and that's why I can't really make you expected to know how to find whether or not it's orientable. For purposes of this course, we're just going to say if it has two sides, inside and outside, it's orientable. That's basically the idea. All right, so this concept of flux is formally just defined this way. So, and it's hard to see probably right there, but just like we did those problems where it's like a line integral f dot dr, and we made the r really bold, right? It's kind of like a vector, right? This notation's a little odd. We talked about where that comes from. You do this with surface integrals, and when you see that double integral over, some s, f dot d, and that's a bold s, that's just what we're talking about with flux. It's just like how we could think of line integrals over vector fields, right? And look at sort of the, correspondence between the vector field, right, and the dot product, direction part, right? So we're sort of comparing a connection between the tangent vector, that's the dr part, and the force field vector, like the vector field arrow, right? That's the idea of the dot product with a line integral. It's just like compare this and see, what the overall effect is. We're just now bumping that up a dimension. And here, it's all based on normals, which probably isn't super surprising because take this. The surface integral is defined with a cross product, which is going to give you, like based on a right-hand rule kind of thing, a normal vector, right, that pops out of the surface or in the surface. And that'll just be dictated based on the sign of the cross product and all of that. So, and that's just what flux is. That's a fancy name for a surface integral over a vector field, okay? I wanted to show you a little bit about how we can sort of simplify this and another way to write it. So n here is a unit normal vector, okay? So n is just given by that. This is what n is. It's just the vector that pops out of that cross product. And so if we just go and plug this in for n, okay, we would get this. This part in here is my ds. This is ds, which we have gone, and there was like a time way back here that we showed it in a previous video. But that's the ds part. And then, this is f parameterized, some parametric surface in there. And so you can go ahead and you can start to cancel some stuff. You cancel that and that. And so what we get for how to compute these surface integrals over vector fields is all of this just simplifies to this, that thing. So yeah, that's basically how you would compute flux. That's what all of it simplifies down to. So you would have to find a parameterization, you plug that into f, and then you'll have r with respect to u, r with respect to v. You cross that, you're going to get vector, right? And then you just dot those two things, and you take the double integral of the resulting thing. It's kind of a lot of work, but that is basically how you do it. And luckily, a lot of those computations we should feel pretty comfy with. So I just wanted to show you doing one of those here. So if we were doing, checking the connection between this vector field and the unit sphere again, the parameterization we should use is the same one we used in the previous problem a few problems ago, just spherical coordinates with rho equal to 1. Then you would have to go and parameterize f. So, I'm putting this in for z, right? Y is y, and then in the k component I put x. So we also need, this cross product with respect to my two parameterizations. So were my two parameters. And so you have to take r with respect to phi and then r with respect to theta. Then you go and cross them, right? So it's quite a bit of work. If you cross them, you would get this. And then now you need to take a dot product. So in order to do these flux integrals, you need to dot product this now with this, okay? So if we do that, we would get this. And then, finally, after all that, that is the thing that you would need to take a double integral of, okay? So the setup of the double integral would be like this. And then it's a lot of trig identities and things again, but you're going to get 4 pi over 3. So there's a lot of work to do these problems. Lots of setup. You got to do the parameterization, which sometimes can be really hard. Plug that into the vector field. Take a cross product of the derivatives of these with respect to the two parameters. Then you got a dot product f with respect to r, f of r, and that cross product, and then do a double integral. So it's a lot of work. But it is fairly normal stuff, just takes a while to go through all those computations. There's one more thing I'm going to say, but it's going to take another video really quick, but it's also going to take only 2 minutes. So I'm I'm going to end this one here, and I'm going to add one more thing in the next video.